Hi, welcome back. This is lesson 5 in unit 6 of Algebra 2. Today we're going to talk about a really super important concept. This is solving quadratic inequalities. We're going to be looking at inequalities of one variable. This is a skill that everyone really needs to get down in their algebra and their pre-calculus courses because it's so important in calculus and higher math. So we'll take it slow and we'll do our best. It's not easy, but once you get it, I think you'll be able to keep it and use it and never forget it, hopefully. So here we go. Um, Example 5.1. We're going to factor the quadratic inequality and use the graph provided to solve the inequality and graph the solutions on a number line. So the problem we have is that inequalities they're not what we call equivalence relations. They don't have all the nice rules that the equal sign and a few other relations in math have. For example, they don't have symmetry, meaning that, if I say 3 is greater than 2, I can't just rewrite that like I could with an equal sign, right? If I say A equals B, I can say B equals A, and that's the same thing. So they don't follow our nice rules, and because of that, we have to keep making adjustments. You remember when we solve linear inequalities, we had to flip the direction of the inequality symbol, the angle bracket or alligator looking thing, anytime we divide by a negative. Well, with quadratics and other higher order equations, we just simply can't do that. So we're left with simply testing regions. But don't worry, it's not as hard as it sounds. So here we go. All right, so let's factor. All right, that's going to have to be a 2, and that's going to have to be an x, right? And we'll do a 3 and a 1. I'll make that a -3 and a +1. Okay, so we have rewritten this expression here, factored. Let me just check the inside and outside product. That's a -6x plus 1x is -5x. So this should be good to go. Now, the zeros of these factors are going to be -1/2. So I'm just going to put that right here. -1/2. That's what that is right there. And the zero of this factor is +3. Well, we can see that. That's why we studied the relationship between zeros, factors, and x-intercepts. We can see that right there. Well, what this inequality is saying is it's asking, when is 2x squared minus 5x minus 3 greater than 0? That means, when is y greater than 0? Because we graph y equal to f of x. The y values are the result of 2x squared minus 5x plus 3. So we need to read this as saying, when is graph above the x-axis? So the equation 2x squared minus 5x minus 3 being greater than 0 means that we are above the x-axis. And you can see that that's happening over here. This is where the graph is above the x-axis. So that's this, and then it goes down below again. So this region on the number line, these x values over here, we are above. So I'm just going to mark that with a plus sign. We're above. And over here, we're also above the x-axis as well. So where are we above? We are above here. So our number line includes the x values that correspond to places where the graph, if we take it up to the graph, that graph is above the y-axis. And that's what it's all about. And then we can simply state our value here. I think an interval notation would be the easiest, -infinity to -1/2. And then we can use the union symbol, 3 to infinity. And that's it. All right, I would like for you to pause the video and give this one a try, please. Okay, let's see how you did. Well, let's see here. We should hopefully be able to factor this. It looks like we can. I'm going to factor out a negative first. So I'm going to say negative, and then I've got 3x squared minus 4x minus 4. and then I'll factor that like this. I'll say 3x and x. You didn't have to factor out that negative. You can factor it, not too hard with leaving it in there. I just always like to bring it out. Let's see here. I think we'll do 2 and 2. That sounds good to me. Minus 2, that would give me a negative 6, and then plus 2x give me a minus 4x. So that looks good. So it looks like the zeros, where this is equal to 0, are at negative 2/3. So that's like right here, right? Negative 2/3. Does that seem reasonable there? And then again at positive 2, that would be the 0 there, right? I think that makes sense. And we can see from the graph that we are above in between, right? That's where the graph is above, is in between those 2 points. And that's exactly what this inequality is asking. Now, don't think it always asks for above. I just happened to ask that 2 straight times in a row. Maybe I should have mixed it up, but I didn't. So, yeah, above, right there. Okay? And so that's going to be our solutions. We're going to be negative 2/3 to 2. And you'll notice I'm using open circles here because this is strictly greater than 0, not greater than or equal to. That could change. It just, depends on the situation. So we'll get to that. All right, let's solve the following inequalities by testing regions on a number line. All right, I've got x squared plus 2x minus 8. So we're going to try and do this without doing the whole graph. So first I'll factor x and x. And I'm going to put plus 4 and minus 2. Now you can see that the zeros of this must be negative 4 and positive 2. That's when this expression equals 0. Well, actually, I'm going to color those in to indicate that they're solutions, because that's what makes this value here, this expression, equal to 0. And as you can see, that's less than or equal to. So we definitely want that part of our solution set. Now, there's a couple different ways you can think about this. You can imagine that this is an x-axis, okay? And you can imagine there being another y-axis. And you can think about the shape of the graph. Because this is a positive x squared, we know that this graph would have to go something like this. And the question is asking me this. What does that mean? Less than? That means y below. So we're actually interested in this middle part here. But I'm going to show you a little bit different way of doing that, since it does say testing regions. And I'd kind of like you to do it both ways. Use your intuition of the graph to help you do it. But when we get to harder equations, you may not be able to graph it in your head. So let's test regions and see what I mean about that. Well, there's 3 different sections of this number line. We just need to try each one and see if the number is positive or negative. I'm going to start with the region over here. 3, 4, 5, and all the numbers in between and beyond. And I'm just going to pick a number, say 4. And I'll plug it into the factored expression. 4 plus 4 is 8. 4 minus 2 is 2. I don't even care. That's 16. Sometimes it's hard to figure out exactly what the number is, but I really don't care. I just care if it's positive or negative. This is a positive number. And you can even mark it on the number line, but notice it's not what we're interested in. We're interested in when we're less than 0. Let's try a number in between. 0 is always nice and easy to do. So let's try 0. If I try the number 0, again, I'm going right there, okay? So 0 plus 4 is 4. 0 minus 2, well, that's negative. A positive is a negative is a negative, right? And lastly, let's try a number to the left of negative 4, like negative 5. That'd be like negative 5 plus 4 times negative 5 minus 2. That's a negative 1 times a negative 7. That is a positive number. So that's positive over here. We're looking for when are we less than. That means below, right? We talked about that earlier. And just like the shape of our graph, remember we imagined that the shape of this parabola, because the x squared, the leading coefficient, is positive, we imagined it would be below the x-axis in between there. So any way you want to get to it, the answer is bracket this time, negative 4, comma 2, because we're including them. All right, let's do this next one. All right, this is 3 minus x and 3 plus x. Greater than or equal to 0. The zeros here are going to be at 3 and we're going to color them in, and at -3. And we're going to simply, let's test some regions here, okay? Let's try the number 0 right in the middle. That'd be 3 minus 0 is 3. I'm trying this 0 here, okay? 3 plus 0 is also 3. That is a positive number. Let's try the number 4. So I'll try the number 4. I'll use a different color. Number 4, plug in the first factor. 3 minus 4 is a -1. 3 plus 4 is 7, so that's a negative number. Lastly, let's try -4. 3 minus a -4 becomes 3 plus 4. That's 7 times 3 plus a -4 is a -1. That's a positive number times a negative number is a negative number. So you can see that this graph, it must have gone up at -3 and then back down again at 3. So, switching direction somewhere in the middle. We're looking where are we greater than 0. That means above the x-axis. So that's this here. So our solution is -3 to 3. All right, let's do another one. Ooh, this one's a little different because it's not set in relation to 0. Well, we're going to fix that first off. Let's fix that. I'm going to subtract the x over. I'll subtract the 4 over. I think I'll also divide everything by 2. As long as I'm dividing by a positive number, it doesn't change any sign. Okay. And there we go. Okay, and this does not look like it's going to be doable with factoring, so we're going to have to use a quadratic formula. And we are going to want to let's get a decimal on these, okay? So our quadratic formula will be x is equal to opposite b plus or minus the square root b squared minus 4 times a times c all over 2a. All right, so we'll go ahead and get a decimal approximation on this. So I'll just pull up a calculator right quick. So this is the square root of -2 squared minus 4 times 1 times, we say -2. That's the discriminant part. You can see what that is. It is a positive number, so we're good. 2 plus, and I'll put the whole thing in parentheses. Let me drag this over so you can see what I'm doing. And then I'll divide that whole thing by 2. So that's the first answer, 2.723. And the second answer is that. So -0.732. So 2.732. And what we say, -0.732. So they're somewhere around here and around here. And this parabola is a leading coefficient that is a positive number, so I think you can see that it is definitely going to be opening upwards like this. We're looking for when we're above the x-axis, that's over here and over here. It's going to be a lot more work to test regions on this one. Plugging in a 0 is pretty easy, though, because you get 0 minus 4. This middle region is clearly negative, and then the other two would end up being positive. So -infinity to -0.732, and we're going to combine that with 2.732 to infinity. All right, let's try the next one. All right, this is also not factorable, so we'll do x equals opposite b plus or minus the square root of b squared minus 4 times a times c all over 2a. Now that's -3 squared is 9. That's 9 minus 20. That's a -11. So this has no solutions, right? So it never has any zeros. And because it never has any zeros, we know the graph is either entirely located above the x-axis or entirely below. So which one is it here? Well, because the a value of this parabola is 1, a positive number, it's going to have to open upwards. And if you're going to open upwards and never cross the x-axis, you must be up above it. We could also simply test a region, plugging in 0, 0 minus 0 plus 5. this graph is positive everywhere. So it turns out the solution is all real numbers. Or you could say negative infinity to infinity if you might like drawing little infinity symbols. All right, I've got a few practice problems for you to do. So give those a shot, please, and then we'll go over them. I'm not sure what this little rogue 9 is doing here. Let's get rid of that. There we go. Just a little extra number for some reason. Okay. Let's see how you did. Hopefully you set this equal to 0. And this one factors as x minus 4, x plus 1. And so 4 and negative 1 are zeros. And this graph we're looking for when we're above the x-axis, which you should have distinguished was over here. Check on a graph if you're not sure, or just test your regions. So negative infinity to negative 1, and 4 to infinity. All right, this one over here I think is also factorable. I'm going to factor out a negative. I get x squared plus 2x minus 15. And that gives me x, let's see here, I think I can do plus 5 and x minus 3. So 3 and negative 5. Because this graph is opening downward, though, it must go like that. So it must be below the x-axis. Oh, sorry, this is actually saying 0 less than. So this is actually saying above. So that's going to be in this region here. Or in other words, when is this positive? You could also test some numbers, plug in 0 for x, either in the original or in the factored, but you'll get a negative times 5 times a negative 3, which 2 negatives make a positive when you multiply. So anyway you shake it, it's in between those two numbers, negative 5 to 3. All right, and then we have these to do. We're going to have to use the quadratic formula here. X is equal to opposite b, plus or minus the square root of b squared minus 4ac all over 2a. So if you'll allow me to run that in a calculator right quick, that's going to be, these numbers aren't too hard. We can kind of do some of our head. That's 36 minus 16 is 20. So that's just plus the square root of 20 over 2 and negative 6 minus the square root of 20 over 2. So 0.764 and 2.36. So negative 3.236 and 0.764. Negative. Okay, both negative actually. And because of the shape of the graph, or by plugging in points, if you plug in 0, you'll get 0 plus 0 plus 4. This part here is clearly positive. We're looking for when, this is bigger than 0, so we're looking for this to be above. That's over here, and then it'll also be over here. So negative infinity to negative 3, union. Oops, that's not negative 3. I'm sorry about that. That's negative 3.236. And that's union negative 0.769 to infinity. All right, on this problem over here, we'll just simply factor out an x. So I get x times x minus 7 is greater than or equal to 0. Remember, always factor GCF first. So 0 is one of our values, and 7. Oops, don't have enough room on my number line there. 7 is one of them. And we're going to be above the x-axis on the left and on the right if you plug in numbers or think about the shape of that graph going like this. All right, so the answer there is negative infinity to 0 with a bracket, union, bracket 7 to infinity. All right, let's practice stating the domain of some of our functions. The domain of a function is all real numbers that result in a real number output. So we start with negative infinity to infinity, or all real numbers, and we remove anything that causes us to either square root a negative number or divide by 0. As you can see, this has a square root in it. Because it has a square root in it, we need to only include the values that result in 16 minus x squared being square rootable. 16 minus x squared is square rootable as long as that value is greater than or equal to 0. Well, we just practiced solving these things, and you get 4 minus x, 4 plus x, which on a number line gives me zeros at -4 and 4. And so you can see that we actually need values. Let's see here. Let's test regions here. I'm going to plug in a 0. If I plug in a 0, I get 4 times 4. That's positive there. Then it's negative here and here. So it turns out our domain is simply -4 to 4. And that actually makes sense because this is the equation for a semicircle of radius 4. And just so you can see it there, you can see it's a semicircle of radius. Oops, I'm not zooming in the right way. There we go. Pretty cool, huh? And so, yeah, the domain is limited just to that region. All right, now in the next one, we need to see the domain is going to be found. That was our domain. The domain is wherever x squared minus x minus 12 is greater than or equal to 0. Well, that's going to be at x minus 4 and x plus 3. Let's see here. Let's factor it. And we get 4 and -3. And so this is actually positive here and here. So my domain is -infinity to -3, union 4 to infinity. So if we graph this one, we should see a gap in the middle of our graph. So let's take a look at that. Y equals the square root of x squared minus x minus 12. And you can see, there you have it. Because this is part of what's called a hyperbola. And we'll learn more about those later. Isn't that kind of cool, though, right? Okay, last we have g of x equals 5x divided by x squared minus 3x plus 2. We don't have any square roots, but we have division. So x squared minus 3x plus 2 cannot equal 0. If it equals 0, then this is undefined because you can't divide by 0. So I'm actually going to solve for what x can't be. And this is factorable as x minus 2, x minus 1. So I get x equals 2 and 1. What that means is that if x is 2 or 1, then we get a divide by 0, which is not allowed. So my domain is all real numbers except 2 and 1. And let's check that now. And we said everything except for, what did we say? Except for 2 and 1. Well, it looks like there's nothing in between 1 and 2. But if we zoom out enough, I think we'll see, yep, sure enough, there's this little branch down here in between 2 and 1. Kind of tricky, right? But there's a gap in our graph, right? There and there where it splits apart. All right, so next is some practice problems for you to do. Good luck on those.